The graph pictured shows the position versus time for an object. The motion here is fairly complex because we see that it's not just a horizontal line or a straight line even. This is a curve. So there's a lot going on with this object's motion. Now I'm going to do the first derivative test and the second derivative test. I'm going to sketch what we call the velocity of the object. So when you have your position versus time graph, his derivative is going to be what we call in physics the velocity. And that's going to have the letter just v. And his units will be meters per second. And then what we're going to do after that is we're going to go even further and sketch the derivative of the derivative. In physics, this would be called the acceleration. And it has the letter A. His units will be meters per second per second. And then we'll talk about what these graphs tell us about the motion of the object. So first of all, let's expand this because we haven't studied how to differentiate a complicated expression like that yet. You would use the chain rule, that's right. But I'm not expecting people to be able to do that yet. So what we'll do is let's write out the meaning of t minus 2 cubed, which is t minus 2 times itself. Then we'll be able to get it into a form where we have just an addition and subtraction of some terms. Be a lot easier to work with. Alright, so I'm going to let this guy here just be a spectator for a minute. I'm going to FOIL this. So we'll do t times t and t times negative 2 and negative 2 times t and negative 2 times negative 2. The t minus 2 at the end can stay, and we'll get t squared minus 2t minus 2t plus 4. Simplify it a little. At that point, we have to send the t to every term, and we have to send the negative 2 to every term as well. So we're going to get t cubed minus 4t squared plus 4t minus 2t squared plus 8t minus 8 plus 3. Okay, I think that's what I get. I'll combine the t squareds together and the t's together, getting t cubed minus 6t squared plus 12t minus 5. So what I want to do next is let's differentiate each term to find what we would call x prime, which is going to be called the velocity function. So it's going to be x prime is going to be 3t squared. I'm bringing the 3 down, subtracting 1 from his power. We're going to get minus 12t plus 12, and that's it. Okay, now the next step for the first derivative test is set your derivative equal to 0. You now want to solve that. So you could factor it. That's one option. You can also make life a little easier here by dividing all terms by 3. Easier to work with now. And you could factor it into 2 binomials. That's one option. You may want to use the quadratic formula instead. That's an option as well. In this case, looks like our combination here would be t minus 2 and t minus 2. They would multiply to make t squared minus 4t plus 4. I would now use the zero factor law, which says that either t minus 2 will be 0 or the other one would be 0, but of course they're the same, so you can get the same solution. Clearly t is 2. Now that is known as what we call a critical value. It is the possible location of a local max or a local min, but not every critical value ends up being an actual local max or local min. In order to determine whether it would be, what we do in the first derivative test is we experiment with values of t that are around 2, such as 0 or 4, and we know that the sign of our first derivative at 2 is of course 0 because we had set it equal to 0 in order to find 2. We want to know what's the sign like to the left and right of 0. So I could go back to the derivative formula. Derivative formula was 3t squared minus 12t plus 12. And I can plug in these various values of t into that derivative formula and see what I get, see what the sign comes out to be. So I'll come up with a chart here of 0, 2, and 4 being the inputs that I want to test. And let's find x prime of 0. It's positive. So our derivative then has a positive sign here. And because there's only one critical point in the whole thing, it's going to be positive everywhere. If we find x prime of 2, I already know what that's going to be. It's going to be 0. And then let's find x prime of 4. Yeah, 48 minus 48 plus 12 makes 12. And this is positive as well. Alright, so that's an interesting result. What the positive derivative means is that the original f of x is sloped up here. And the positive on this side means f of x is sloped up there as well. Now, if we look at the picture of f of x, we can see that that is the case. That we have a positive slope here to the left of 2, and we have a positive slope to the right of 2 as well. But the slope at 2 is 0. It's a nice horizontal tangent line there. So the type of point we have would be called a stationary point. It's called stationary because the object is at rest for just an instant. But it's not a min or a max. Now we can graph the derivative. I already have a bunch of values that I could use to graph it with. We could use this 0, 12. We can use 4, 12. And this 2, 0 as well. And I better plug in like a 1 just so I can graph it a little better. So that's 3 minus 12 makes negative 9 plus 12 would be positive 3. And x prime of 3 by symmetry is also going to be positive 3. He's just going to look like that. Okay, so where x prime touches the horizontal there, that's a special time for the motion of this graph. What it indicates is the object comes to rest for an instant, and then after that it continues moving. So that's the first derivative test. We see that positive values here correspond to a positive slope in the graph above. And positive values over here also correspond to a positive slope in the graph above. But here we have a 0 for the derivative, and that is a place where our object is just at rest. Next, we got to do the second derivative test. So my first derivative was 3t squared minus 12t plus 12. For the second derivative test, we have to find the derivative of the derivative. We have to find what we would call x double prime. In this case, this is going to be the acceleration. That's the term that's been given in physics to the second derivative of the position. So let's differentiate once again. The 3 can be like a spectator here. He can just come down, and then he'll be multiplied by the derivative of t squared, which is 2t. When we're taking the derivative of a number times a variable, it's going to be just the number. And that's it. Derivative of a constant is 0. So we're looking at 6t minus 12 is our second derivative. You want to now set your second derivative equal to 0 for the second derivative test. And we'll solve once again for any points that might be important. We're going to solve for any possible locations for points of inflection. The second derivative tells us about the curvature of the original, whereas the first derivative told us about the slope of the original. So let's solve this. We'll get 12 equals 6t. T equals 2 is a possible location for the point of inflection. Now, just like with the first derivative test, what we can do is make a number line for different values of t, and then pick some that we want to plug in around that time. We're going to be looking for the sign of the second derivative here. I already know the sign of the second derivative is 0 at 2. But what is it around the 2? So we can use our formula, pick arbitrary values of t that are around 2, and we'll plug in to the second derivative now. I get a negative result for the time of 0. And what that's going to indicate is that our original graph, f of x, it's going to be concave down for that interval. X double prime of 2 is of course 0, and let's find x double prime of 3. I get 6, which is positive. So what that's going to indicate is that f of x must be concave up on that interval. Let's see if that matches up with what we see in the picture. it does match up. We see here that there is a frown or an upside down U shape. That indicates that the graph is concave down on that interval. And then here we see a smile or a right side up U shape. That tells us that we're concave up to the right of the 2. So this is a special situation here where there's a stationary point and a point of inflection in the same location, because a point of inflection is where that concavity switches. Let's graph the acceleration function. I have some values I can do it with. I can do it with 2, 0 and 3, 6. It's just a linear function. There we go. This is called x double prime of t. We have to be able to find the locations of any mins and maxes or points of inflection. Here we didn't have a min or a max at all, but we do have a point of inflection. So the way to find that is we know that the point of inflection occurs at t equals 2. So what we can do is now plug that 2 into the original function to find the location of the point of inflection. So I would do x of 2, which is going to be 2 minus 2 cubed plus 3, which is just 3. So now your 2 and your 3, they go together to make the coordinates of that point of inflection, 2, 3.